This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
And lastly, well, suppose I didn't want the maximum gain and I wanted some other gain, you know, what are some potential impedances, input or output, matching networks which give me that. And that's it, right? So quite easy. It shouldn't be too difficult. You've gone through it many, many times. What's important, however, is that you show you're working out. Now, if you just give me an answer, I'm going to get very suspicious, right? So if you give me an answer without any formulae or without any working out or without any justification, well, I might not be able to do anything in the sense that, hey, I haven't caught you cheating, so I can't do anything. But if it's wrong, you get 0. You do some working out, and you show me that you maybe pressed the wrong button in the calculator, you get something for it, right? And that's what I'm trying to say, that you've gone through the process and you can actually go through and understand those things. But they're the major concepts that I need you to understand from this course. And then on top of that, what we will need to do, like for the final year exam, we will need to include things like noise figure and things like that as part of the the final exam, where if you're building a power amplifier, you want to, or a low noise amplifier, you need to know how to make something that's also got certain noise characteristics or noise performance envelope, rather than, hey, this is how I achieve maximum gain or I achieve some gain, right? But that's definitely not tested. The noise figure is definitely not tested, not part of this test, but you can be pretty sure that it will be part of the final year exam. Okay? So you know all that. I think you've done quite well for the RF part of the course. You've learned quite a bit. Now, you need to be able to internalise it. You need to be able to explain it. There might be some questions like, explain this, rather than I'm copying a formula and I'm just showing you a formula. So that's what I want from the test. Just, hey, you've actually done some reading. You've learned something. So you haven't wasted your time. I haven't wasted my time. So we've all learned something about these important RF concepts. Okay. Any other questions as it relates to the test? Yes. I've made it open book. I've actually been successful in making it open book. So you can actually bring anything you like. All right, now the final year exam is going to be closed book, and then I'll have to give you formulae. But yeah, just what I would suggest is, you can bring your materials, but just, write down on a piece of paper, hey, how do I work out stability of a power amplifier? How do I determine, if I'm doing matching, what do I need to do? What's the input and output impedance? Input and output reflection coefficients in terms of the scattering parameters. How do I work out whatever? Stability circles. How do I work out the gain circles? I mean, I've pretty much given you the questions, right? So you just need to now know how to use it, and then also, if I'm asking you a question about what does this mean, be prepared to answer. But it should be, I genuinely think it should be pretty easy. I think you should all do quite well. So I wouldn't stress too much about it. Just revise, and also just, it's deliberately made a little bit long. I've deliberately made it a little bit long, just so that I can't get everyone getting 100%. All right, so I've got to try to distinguish between individuals, right? So I've got to get some kind of distribution, right? So I've made it a little bit long. It's not too bad. I mean, you should be able to get through it pretty quickly. But what what I would suggest is be familiar with the concepts, because you know, like if I gave you enough time, you know, you can all read a book and you can all should be able to all work it out right anyway. Right? And you've gone through it. So it's going to be a question of, hey, have I really learned this? You know, can I know where to find, you know, how to determine stability, how to work out my, you know, gain circles, how to work out my stability circles, what does it all mean, kind of thing. All right? All right, cool. Any other questions as it relates to the test? So there's no oscillators, there's no noise figure, there's definitely amplifiers and stability of amplifiers. There's definitely matching networks, and there's definitely a question on the antennas. And other than giving you the questions themselves, I don't know what else I can do. All right. Okay. Okay. So now on this lecture, what we're going to do is we're going to transition from our RF section to our digital section. Right. So what we're trying to do now is learn a little bit about digital logic and then high-speed digital logic. Okay. Now, what I'll do is, you've probably all gone through this. I'll talk a little bit about the MOS transistor and details about the MOS transistor and the like. You've probably heard it hundreds of times before, but what I'm going to do is use this lecture as an ability, or take the opportunity in this lecture to go over transistors again. And predominantly what I'm going to focus on in this course is actually MOSFETs. Now, I believe that in a lot of your lectures, people are still focused on BJTs, is that correct? Bipolar junction transistors. I'm actually going to focus on MOSFETs. And the reason why I'm going to focus on MOSFETs is that if you're building any kind of semiconductor product or logic-based semiconductor product, it's going to be CMOS-based. I'd be very surprised if it's going to be BiCMOS, based, or bipolar junctions aren't based. I don't know if there's any recent products that I've seen which are bipolar, the logic's made out of bipolar. Yeah, I mean that was in the 70s or 80s, maybe you would have seen it, but not recently. It's all it's all CMOS based. That's why we're going to focus on the MOSFET. Now, can you tell me, like, if we're going to distinguish between RF and digital, what are the differences? What do you think are the differences from a signal perspective, a real world signal perspective? Don't say to me, digital, everything's 1 and 0, because I'll say, no, it's not, right? You're not actually putting the 1s and 0s. The real world is analog. Right? But what are the main differences? What are the other main differences? Like, if you're looking at the waveforms, they sort of approximate 1s and 0s, right? You're almost dealing with square waves. Now, what's the significance of a square wave? In our RF section, what frequencies do I need to consider? You know, if I'm looking at this sequence of square pulses, what am I really dealing with? Right? In RF, what we were doing is pretty much we were dealing with one sinusoid, right? And if it was at frequency F equals F naught, that's what we were doing, right? Here we've got, in digital systems, we're putting a sequence of pulses. This is just trying to motivate the pain and suffering that we're going to go through now that we're doing digital systems. But here, what are we doing? We're actually essentially transmitting multiple sinusoids, but they're in a particular phase in a particular way. So that if we're looking at a 1 gigahertz signal, you know, of pulses, really the spectral content of that is in the many gigahertz, right? And that's that's the only thing I'm trying to emphasize, that, you know, if you're looking at, say, 1 or 10 gigahertz digital, actually you've got to be doing the design as if you were doing your analog design at, you know, 50 gigahertz, right? You've got to be looking at the third right? And that's something that you need to always be aware of. Now, let me also ask a different question, and this is before we start looking at the transistor itself. When we do analog, we need to already know a lot of times what we're doing is we're doing small signal analysis. Now, that's not necessarily true when we're doing oscillators or when we're doing, you know, power amplifiers, right? But when you're doing small signal analysis, essentially what you're doing is you come up with an approximation for that transistor. We talk about it, and you've seen that approximation numerous times where you've got that every small approximation to a small signal approximation for a transistor. Right? You usually start off with a symbol that looks like this, which is a real transistor, and what we'll do is we'll also talk about, you know, the substrate and the like today. And what you do is you approximate this with the small signal model, right? And, you know, and then you've got, you know, depending if you want to go higher frequencies, you might add some more capacitors here. You might add an output resistor here to contend with, you know, channel length modulation. And you might add a few other bits and pieces, right? But here, essentially, what you're assuming is that when you calculate using that particular model in order to do your calculations, you're assuming that the signal into the gate, or the voltage between the gate and the source, this is source and this is the drain, is actually relatively small. Can we make this approximation here? Can we use that approximation? And essentially if we're looking at voltage levels, we can say, let's say, assume this is 0 and this is 5 volts, or 1.3 or 1. You know, let's go 5 volts, 1.8 volts, 1.3 volts, point or 1.0, which most devices are today, right? It's going full scale, right? We're going from 0 to, you know, to the supply rate. So therefore, this approximation, you can't use this approximation and everything that you've learned on as part of your small signal analysis in digital systems. Okay. So that's the reason why we've distinguished the two parts of the course. One is, hey, we're going very fast, but the signals can potentially be relatively small, so we can start doing these approximations. Even if you remember our low noise amplifier, where what we did is we did some analysis where we looked at both source degeneration techniques, where we added an inductor in the source and an inductor in the gate in order to be able to build a low noise amplifier. Right? All that stuff is great, but it doesn't directly apply when we're doing our digital circuit design. And also what it means is when you're building a microprocessor and all these other things, or all these other digital circuits, you now have you're now dealing with large signals, right? And your transistor is going to go between cutoff and saturation, right? And we'll define what that all means. So your transistor's going from cutoff to saturation, multiple times, very, very quickly. Okay. All right, so let's talk about this wonderful MOS transistor. All right, so we've usually got this symbol, right, for a MOS, and usually everyone draws it as a 3-terminal device. Yes. Oh. Perfect. All right. So everyone draws this FET as this 3-terminal device. Is it actually a 3-terminal device? No. Why not? Sorry? Okay, there's an extra one, but where's that extra one? Right, sure, yes, I know that yes, there's something there, yes, so there's another terminal here, but what does that terminal mean? Well, it's used to signify the type, that's right, and it's not actually used to signify if it's PMOS or NMOS, the type. It's used to signify if it's enhancement or depletion, but usually what it's doing is you're tying something to the substrate. So really, when you're looking at a FET, it is actually a 4-terminal device that you need to consider, right? Okay, so let's look at this MOS transistor, and I mean, the first thing that what we want to talk about is it's a majority carrier device, where, as we've talked many times before, and in ways similar, not too dissimilar to your BJT, where the current in the conducting channel is modulated here, which is different to a BJT, by the voltage applied to the gate. Okay, so what we've essentially got is a voltage-controlled current source. So that's what essentially a MOSFET is, right? What controls a BJT, the current through a BJT? Okay, I've said this is a MOSFET, and we're going to talk about MOSFETs, and MOSFETs are different to what you're used to, which is a BJT. And a BJT, how do you control the current of a BJT? Yes. Yes. You're right, also. Yes. Okay. Yeah. So you put some current into the base, and you've got some a current amplification, a beta factor, and that actually controls the current that you get out of from the collector to emitter, right? So you get a B times the base current gives you the current through the collector, and the total current is B plus 1 times the base current. Okay. Now, in how do you call it? In MOSFETs, there are what I'll call 4 types of devices, but 2 types of carrying current. 2 types of carriers. What are the 2 carriers that you would expect, or you expect? No. Majority and minority are the carrier. Okay, majority carriers is what you. Sorry, electrons and. All right, perfect. All right, so what we've got is 2 broad classes of devices, NMOS and PMOS, and essentially the NMOS device, what actually happens is, or the majority carrier, what carries the current in an NMOS device is essentially electrons. Okay, and in a PMOS it would be. Okay, now the next thing we're going to say, and let me ask you, what happens in a PMOS device, and I don't know if I've probably got pictures somewhere, so I'm probably shooting myself in the foot because I've already put the lecture notes up. So, but anyway, on an NMOS device, essentially what happens is you apply a voltage to the gate, and if you exceed a certain voltage, that increases the electrons in that gate, which actually makes the device be able to conduct the current between its source and drain. Okay. And the higher you increase the voltage past its threshold voltage, and we'll talk about threshold voltage in a little while, the higher the current. Okay? How about a PMOS device? What would we think about a PMOS device? Remember, a PMOS device is holes, right? So that's what's used to carry the current. So if we increase the voltage for a PMOS device, do we expect the current to increase? Sorry, if we increase the voltage at the gate of a PMOS device, do we expect the current to increase or decrease? Sorry? Decrease? Is it increase, decrease? Okay. All right, so who reckons increase? All right, 1. Who reckons decrease? 2, 3. Okay, yes. All right, it actually decreases. And the reason is, as you increase the voltage, you're actually repelling the holes, right? And as a consequence, you've got actually less majority carriers in the actual channel, right? And that's the difference between an NMOS device and a PMOS device, right? And that's a very interesting property that we use, being able to have both NMOS and PMOS devices in CMOS, which is here complementary, is what allows us to build some very low power circuits, right? Because you can actually do a lot of logic design using NMOS, right? But the problem with NMOS is generally that it's essentially very, how do you call it, power hungry, right? And that's why, if you're trying to build high performance, low power circuits which operate on the battery, that's where you always use PMOS, that's why you always use CMOS rather than an NMOS device. Now, let me ask a different question, and I know you guys have all done your device modelling course or subject. Would you expect an NMOS device in the same material, an NMOS device or a PMOS device to be faster? And why? The switching speeds of an NMOS or a PMOS device to be faster. It's NMOS, all right, and so what you find is the mobility of the holes is actually always lower in the same material, always lower than how do you call it, an NMOS or than an NMOS device. And the reason I was mentioning this, but then I felt like, oh yeah, the effective mobility of electrons is always higher than holes, because the effective mass is of the holes is larger than the electrons. But then I was like, oh, that's a bit of a circular argument, right? Because what does a hole mean? Because you're not actually transferring how do you call it, protons. The protons are actually stuck in the lattice, right? So what you're doing is you're moving areas of depletion. But notwithstanding that, usually what happens is essentially PMOS devices seem to be slower than NMOS devices, primarily because of the electrostatic forces associated with, once you've got an electron, the atom tries to hold on to it rather than, if it's got a vacancy, it tries not to let any more go through. Whereas it's a little bit. Anyway, I've got a terrible explanation for that, so I'm going to stop there. Okay, so we said that for NMOS devices, there's a threshold voltage, And for these type of devices, for these N-type devices, we usually define that voltage as the minimum voltage at which the device turns on, right? So if you've got an NMOS device, you need to exceed that particular voltage in order for you to get transfer of current. And essentially what happens is you've generated or have enough electrons in the channel in order to be able to conduct the current. And for a PMOS device, essentially what happens is you're below the threshold voltage, so therefore you've actually caused enough vacancies in order for these holes, or these essentially areas of missing electrons to actually transfer across the channel. And essentially what I'm talking about here is re-emphasizing the two types of devices. There's two types of N-type devices, enhancement and depletion, and P-type devices, again, there's enhancement and depletion. So let's look at this a little bit more in greater detail. So if we've got an N-channel enhancement device, essentially what we've got is at a positive voltage, what happens is the current begins to increase. For an N-channel depletion device, essentially what happens is at zero voltage, there's enough free carriers that the system continues, or there's enough carriers in order to maintain the transfer of current through the device. And essentially what you need to do is take the voltage significantly negative in order to be able to switch that device off. In a P-channel enhancement, essentially what you've got to do is you've got to decrease the voltage below a certain value in order for the current to flow. And the P-channel depletion, essentially you've got to get the voltage high enough in order to stop the flow of current. Now, usually what we're going to see for most of our analysis is, the N-channel enhancement and then the P-channel enhancement type devices. Now, let's look at the structure of a transistor, right? So how does a real transistor look like? Okay, now, what I've done here is, has anyone seen or know how transistors are built? Like, for example, when you're looking at one of these chips in one of these devices, has anyone seen what the structure looks like? Okay. Have people, okay. It's worthwhile just, if you get a chance, see some YouTube videos or something. But essentially what happens is you have a large wafer, right? Usually these wafers are created in large crystals, right, which are these huge things where what you've got is you've got molten silicon, and essentially what you do is you put a little bit of a crystal in there which acts as a seed. Then you start pulling, that seed that's actually beginning to form the crystal out of the out of that molten piece of silicon, and as it cools, it actually begins to form like this large cylinder. And these days, they can actually make these cylinders 12 inches in diameter, right? And that's usually, when somebody says to you, we've got 12-inch wafers, essentially what they're talking about is when they've got this large crystal, they cut these wafers across, and then you've got this, like a dinner plate, you can think of it as a dinner plate, which is 12 inches in diameter, right? So you've got this huge plate now on a crystal, and as part of this process, usually what happens is that it's, in most cases, they're lightly doped with boron in order to make it P-type. Okay. So now you've got this. Now you can think of this being, looking at it on side on. Okay. And essentially, what you do in order to build a transistor, because here, you think of it as, 12 inches, and usually an ARM microprocessor is probably these days 6 or 7 millimeters by 6 or 7 millimeters, right? So you're taking this little bit of area and you replicate it gets replicated many times over, right? On the face of it. Right, and you've got each one of these is 6 by 6 millimeters. Now I can't remember if 386 processor is probably what. Not a 386, but an x86 is probably what, 20 millimeters? Thereabouts. Okay, so if you're doing, for example, your latest and greatest CPUs are probably 20 to 25 millimeters by 25 by 25 millimeters, and they've got at least 8 cores on it. So on this is, you can think of it as 8 little small processors, and they've all been connected together. But essentially, and probably at the moment, probably we're talking about 2 to 5 billion transistors. Right? So you can think of it as this, you've got billions and billions and billions of transistors, probably close to 1 trillion transistors on a wafer. Right? If you were doing, how do you call it? A whole wafer of x86 processors. Okay, so if we grab one of these, chips, and then we look at it in a particular section, right, and we look at a particular transistor, essentially what we're seeing is, so let's grab this section here and then blow this up even further, and let's look at today what would be, say, 10 nanometers by 10, maybe make it 100 nanometers. That would be the size of your transistor. It's probably, usually the channel width's about 7. I've added a little bit in order to add some other stuff around it. And then I've added a little bit more space because you might want a larger transistor that has enough drive. So that's your whole transistor. Now, what does that look like? Well, we're going to look at it here. So essentially what you've done is this little bit, which is, a few nanometers by, a few nanometers. Essentially what we've said is the wafer itself, the whole wafer is lightly p-doped, right? And that's as part of the manufacturing process. And then essentially what happens is we implant phosphorus into these regions in order to make the N-wells. How do we implant? Does anyone know how the implantation process occurs? Yeah, I mean, you've been doing device physics, right? Device modeling, right? So you've been told that you've got an N-type piece of something. So, you've been told it's got N acceptor atoms, all right? Okay, they didn't just appear there. Some deity, like a god, didn't come in there and just put them there. Some human did that, right? So what's the process? No. That's fine. That's when you've got a PN junction. That's what happens. But somehow I've made this p-type, lightly p-doped silicon. It's lightly p-doped, right? And what I'm saying is I've made it from lightly p-doped, and I'm trying to build a model here. I'm trying to build a transistor. What I've done is I've made these regions highly n-doped. Right? How did I do that is the question. Well, how is that done? Okay. Okay, so what would be worthwhile is look at ion implantation. Essentially, all you've done is you get a metal, one of the metals, either, you know, it depends if it's phosphorus or boron or whatever. Usually it's in some metallized form. You put it in an oven, right, and you form a gas, forms a gas. You put it under a high electric field, right, and these essentially atoms, depending on the charge, actually go and smash into, right, you put a mask on top of this, and I won't talk about, you know, generating masks and all that, but essentially you generate a mask, so therefore, you know, if, you know, these other ions hit here, they just hit into the mask, which you remove later on, but they go and implant. You know, it's almost like throwing billiard balls to a surface, right? You throw enough in there, but they actually go and implant in the surface, and that's the implantation process, right? And then what you do is, because you've caused a lot of damage to this crystal, you reheat the crystal in order to do annealing, right? And to actually activate these dopants. So essentially, what you're doing, you're doing this, but you're doing this at the nanoscale, because remember we said that this little 6 by 6 millimeter device, or part of the wafer's got billions of transistors on it, right? And here what you're doing is you're able to do this at a massive scale, right, at a very high resolution. And you know, your latest processors these days, you know, the transistors are 7 nanometers large, right? So you can think of these areas that I'm talking about are probably 1 or 2 nanometers in size. Right? So it starts getting really interesting, right? Okay, so what you've done is you've implanted, and then what we've done is we've removed, you know, the mask, and essentially it's something called photoresist, right? And essentially what we do is, again, we put an oxide here. Why do we put an oxide? Does anyone know? Why can't we just put the metal directly there? Sorry? Okay, because you don't want conduction into the gate itself. You want to make the gate high impedance, right? That's one of the reasons. Okay, and then also metal on silicon, also you get some implantation, which also causes you know, problems, right? So you put an oxide, and then what you do is you deposit a gate. So can someone tell me, and we'll talk about the gate, but can someone tell me what are some of the oxides that people are using recently in order to make transistors? Right, I mean, back in Shockley's day, it would have been silicon dioxide. These days, you've probably heard of the hafnium oxide and things like that, right? No? Okay. All right. So usually what you do is these days people put hafnium oxide there, right? That was one of the large advances, because hafnium oxide's got a high dielectric constant, can be thin, high dielectric constant, you know, and it has low leakage, right? Because as you make this thinner, what you would get is you get tunneling of electrons, and that actually causes you to actually, you know, consume more power, right? So therefore what you want is a dielectric which has very low leakage, and hafnium oxide is one such dielectric. All right, now we're going to make contacts. Okay, so we put an oxide here, we put a gate. Now, usually in the past it would be metal. These days, people use something called polysilicon. Okay, and you can think of it as being an amorphous layer of silicon, which is very heavily doped, right? So it behaves like a metal, right? But it's not. It's polycrystalline rather than monocrystalline like here. So it doesn't have as great properties as this silicon, but for what we're trying to do in this particular case, which is just to apply voltage, it's good enough. Right, and it also means that we don't have to deal with a lot of the issues that we would otherwise need to deal with if we put metal there. Okay, and then what we do is we make the contacts, right? And here, what you need to do is you essentially need to redope these areas to a much higher concentration in order to be able to form ohmic contacts. Right? Why couldn't I just put metal into the silicon? All right, what I'll do is I'll leave that as a homework exercise. Look up Schottky barriers. Okay, I've spent too much time talking about this stuff because I get excited about it, but I haven't spent enough time on this. All right, so essentially, this is the structure of the transistor, right? So what we've got is essentially, just to reiterate, we've got the wafer, we've created two tubs, which are of the N-type. We're talking about an N-type transistor. And what we've done is we've added, in order to make ohmic contacts, we've added another region which is very highly doped. We put the metal on there so that we can form ohmic contacts. And essentially what we've got is, the oxide and the gate. And this is your MOSFET. You're an NMOS MOSFET. Now, there's a couple of things that I want to point out is you've got the other thing that we've got, other than the two terminals, or the three terminals that we're used to, we've also got a substrate terminal, right, which is used to determine the voltage of the actual substrate. And importantly, what we see here is we've got two, and there's multiple ones around them, right, but what I'm doing is drawing them as two parasitic diodes, or PN junctions, right? Why is it important to look at those or be aware of those two parasitic diodes? What happens if my substrate is higher than my source? Current will flow through them, right? And essentially what will happen is you've got a forward bias diode, and essentially what happens is it'll generate a lot, and it'll generate a lot of current, right? And essentially it will wreck your device. So this is what is known as latch-up. When the substrate is forward biased relative to the source, essentially what happens is large currents flow from the substrate into the source through this little tub of material, you can think of it, and as a consequence, that damages that material, right? And that's one of the things that happens during, latch-up, right? Now, if it happens very rarely and not a lot of current happens, you can sometimes you might be able to tolerate it, but generally what you need is the source to always be at a higher voltage than the substrate. Okay, and that's also, when you see a lot of people connecting the MOSFET, on a bulk device, what you actually see is that's the connection, right? So you've actually connected the substrate to the actual source. Now here, what I'm also talking about is I'm focused on bulk devices, right? Now there are some newer devices where people are actually, rather than using this lightly doped wafer, right, what people do is they've got a wafer, there's an actual layer of insulator, and what they then do is deposit materials on top of that, and that's usually called silicon isolator. It's a lot more expensive, but it has advantages in terms of latch-up. And it also has better high-frequency performance. So the way that the device operates, this MOSFET operates, is essentially we apply, as you can see here, when there's no voltage or between or even if there's a voltage between the source and drain, or, you know, irrespective of the source or the drain being, you know, whatever their relative voltage is, unless there's a voltage on the gate, essentially what you can see is you've got two back-to-back PN junctions, right? So therefore, that's why current won't flow, right? So if you've got nothing on the gate, you can almost think of it as NPPN, right? Diode, so therefore nothing will flow. And essentially what you need to do is, as the voltage in the gate's increased, what happens is electrons begin to are attracted to the gate interface. There's a little bit of depletion in the channel, and when you get enough of those electrons in the channel, what you've got is the ability for current to flow. Right? So therefore, when you exceed the threshold voltage, you now have a device which, you know, has enough of these carriers, which now allows you to conduct a current. And the more positive you make the voltage in an NMOS device, the larger the current. Okay? Now, what I've gone through here is gone through and talked about the threshold voltage, and essentially what I've been doing is trying to go through and explain how the threshold, how you derive the threshold voltage in terms of properties of the actual semiconductor. All right. Now, question: have you gone through all these equations in your device modelling? Okay. So what I'll do is I'll continue for another 4 minutes, and what we'll do is we'll continue this in the next lecture. But essentially, what I'm doing here is going through and saying, well, this threshold voltage can be derived as a function of the ideal voltage of an ideal capacitor at the gate plus this concept of a flat band voltage. And what you can actually show is that this ideal threshold voltage can be written as Boltzmann's constant, temperature, electron charge, and the log of the acceptor versus the intrinsic concentration of carriers in silicon. C is the C oxide, the capacitance of the oxide, and then what you're able to do is actually go through and work out what you would expect your threshold voltage to be. So this isn't the reason why I'm going through this for you is actually to show you that there's this concept of threshold voltage which we've described, but also that threshold voltage depends on, and as we'll show, depends on the substrate or the source to body voltage, right, or source to substrate voltage. Now I've called it VSB rather than VSS, so that it doesn't confuse you with the source. But VSB is the source to base voltage, right? And essentially, the reason why I've gone through this is actually to show you the following type of device. And here, all I've done is shown you that, hey, let's now look at the situation where we've got two transistors, right, and we've stacked transistors. Now, why might we want to stack a couple of transistors? Well, if you're building an inverter, right, you've got a PMOS and an NMOS device, or if you're trying to switch a voltage which is greater than, for example, your supply voltage is greater than the voltage that, the maximum voltage of any one transistor, one of the things that you can actually do is put two transistors in parallel, so, the voltage across any one of them doesn't exceed the maximum. Right? That's one of the tricks that you can do. But the point here is as you do this, what you start seeing is that in this particular case, the substrate to body voltage is zero, but it's not necessarily hit zero here. And as a consequence, if you go through the calculations, what you're able to show is if you do this, you get this effect called the body effect, which is essentially all it's doing is increasing your threshold voltage. Right? So if you start to playing this trick, you might be able to get away with saying I can add two transistors in parallel. Parallel is not the right word, in series I should say, or you stack these ones. But if you add 3 or 4 transistors, the issue is, body effect starts becoming more and more predominant, and as a consequence of that, what happens is that your threshold voltage changes, and after a while you can't do that anymore, right? You don't get any more gain in doing this, or actually setting it up in this particular configuration. And the other reason why I wanted to bring this up was also, other than for logic circuits, this is one of the tricks that you can also use if you're trying to build, for example, power amplifiers, right? The output of a power amplifier at low frequency is V squared on RL, which is V is the voltage that you can actually swing, right? So if you've got a transistor which is, say, for example, got a 1 volt maximum, if you put 2, right, you've got 2 volts that you can actually swing, but what happens is, you can't actually go all the way up to 2 volts because, all of a sudden your threshold voltage it starts to increase and you can't actually do that. So maybe you'll go to 1.5 volts, but nonetheless 1.5 volts squared is at least a significant increase relative to, if you only were able to swing 1 volt. And this is an important trick that you use when you're trying to build, amplifiers or other types of components on a chip. All right, and I think I'll leave it at that. And then what we'll do is, so the next lecture, what I want you to do is, other than study for your test, because I know your test is coming up next week, what we'll talk about in our next lecture is we'll go into details about the CMOS inverter. Right, so what I would like you to do is, who knows what an inverter is? A logic inverter. Sorry? I'm sorry, I'm deaf. Perfect. Okay, so change the logic from 0 to 1 and 1 to 0. Have you seen one built? How would you build one? If I gave you 2 transistors, I said to you, you've got 2 transistors to build, an inverter. What 2 transistors would you use? All right. In the notes, what we'll do is we'll talk about it next week, but think of the following situation. This is a PMOS device, right? That's why I put that. So we'll say PMOS. If you want me to, I'll connect the substrates for you also. This one's an NMOS. All right. So think about this device, and what we'll do is we'll analyse that device in our next lecture. All right, because there's a lot of very interesting things, even though it's one of the most simplest logic gates, there's a lot of interesting things that we can actually get insights from using this device. And this is an inverter. This is literally how you would build a CMOS inverter. Okay. What are some other gates that you might use? AND gate, OR gate, yep. XOR gate, yes. So you're talking to me all about asynchronous logic elements. What's a D flip-flop, JK flip-flop, Q, what are all that? Have you looked at any of those? Yes, no? Who's seen a D flip-flop before? Okay. What's it used for? I guess you can use it to synchronize, yeah. I mean, and you can also use it as SRAM, right? You know what SRAM is? From Right, so you can actually, so you all know about DRAM, right? DRAM is usually what's in your computers. It's usually made as like capacitive, it's almost like little capacitive elements. SRAM is D flip-flops, and essentially what you do is you use that to actually store data. Super fast, but also larger, you know,